All right, so this is the second half of the practice final exam for Chem 1151. We're starting with number 25. So balloon has a volume of 5 liters, so that's a V, and 22 Celsius, that's a T, and 1 atmosphere, that's a P. And then they asked me what the new volume is, and so now these become 1s, and this is a 2, and this is my P2, and this is my T2. And so I'm doing the PV-TiNi, the combined gas law. But they didn't give me anything about moles. That's okay. I can just erase or cross out moles. The next thing I want you to do is to cross multiply always when you're using PV-TiNi, because a lot of people have trouble solving algebraically with fractions. So I would cross multiply first. We're trying to find V2. So now it's a lot easier to solve for V2. And then we can just plug in. Now we want to make sure we have a units correct. As long as volume is the same for both, which it is, and as long as pressure is the same for both, which it is, we don't have to change that, but we always have to change our temperature. And actually, I'm noticing now the temperature is 22, so I can actually, it stays 22, so I can actually get rid of the T's. We can, let me get rid of them this way. We can get rid of the T's because the temperature stays constant, so it just cancels out anyway. So we have P1 times V1 over P2. That cancels out my atmospheres, leaves me with liters, and I should get 1.67 when I do that math. All right, we have a volume, we have a temperature, and then we want to know what new temperature, so now these become 1s. And then volume half as large, what would that V2 be? If the first volume is 500, what's half of 500? 250. So when we're doing volumes, as long as it's the same unit on both sides, that's fine. But when we're doing temperatures, we always have to plug in Kelvin. Even if they want Celsius at the end, you still have to plug in Kelvin to do the math. So we're going to use PV-TiNi. And they don't give us information about moles, and they don't give us information about pressure. And then I can cross multiply. And then I'm going to solve for T2. And then once I have Kelvin, I can plug in my T1. My V2, I said, was 250. And then my V1 is 500. This cancels out the milliliters and gets me Kelvin. Now, you look at all of your answer options, and they are in Celsius. So we just have to go back to Celsius. Now, I know you may be thinking, well, if it's in Celsius, can I just put in Celsius? Try it. Put in Celsius, put in 20 degrees Celsius, and see what you get out. You're not going to get the same thing. The gas laws only work in Kelvin, so the relationships, the proportionalities only work in Kelvin. So you have to turn it to Kelvin when you're doing the math. That's just, them's the rules. So we get negative 126.5 or negative 127. Which of the following is an exothermic process? So exothermic means give off heat. It also, we can think about it as making particles closer together. So making particles closer, we're slowing them down. So we're thinking about going from something like this to something like this. So if like this was a gas, this is a liquid, or going from a liquid to a solid. So that would be exothermic, because the opposite is endothermic, right? Going from solid to liquid is melting, that's endothermic. Going from liquid to gas, that's boiling, that's endothermic. And so the opposite is exothermic. So sublimation, that is solid to gas. So that would be exo. Melting, that is solid to liquid. That's exo. Evaporation, that is liquid to gas. That's exo. So the only one that's different is condensation, which is gas to liquid, which is endo. All right, so the relationships in a chemical reaction are not in grams, so I'm going to go ahead and get rid of one. They can be in moles or they can be in molecules. So 2 and 3 can be fine. So the reason why it would be the same number of moles and molecules is because Avogadro's number conversion is the same for molecules and atoms to moles. So we can say like 3 moles of A, 2 moles of B, 1 mole of A, 3B, 2, or we can say 2 atoms A, 2 atoms B, 1 molecule AB, 3, 2. As long as it's either in moles or particles, that's fine, but definitely not grams, because grams are not related by the same conversion factor with each other. Which is the correct Lewis structure for H2CO2? So let's just go check to see if everybody has an octet, and we can get rid of some that way. These oxygens have 2, 4, 6, so they don't have an octet. Here, this one B looks okay. We'll have to come back and check it. This one doesn't have an octet. This one D looks okay. We'll have to check it. This one doesn't have an octet. So we down to these two that actually have octets, and we need to count electrons at this point. So how many electrons do I need? I have 2 H's, so that's 2 electrons. I have 1 C, that's 4, and I have 2 O's, that's 12. So we have 18 we have to give out. So let's just count here. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right. 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18. So they both have 18. Which of the following would be the more correct structure? So we have to make a choice here. Do you think it's better for carbon to have 3 bonds and a lone pair, or for carbon to have 4 lines? Think about the most common way you see carbon. So on the final exam, you probably won't see 2 that are this different, but carbon likes to have 4 bonds. So can we have this structure be, it's not an incorrect structure. Everybody has octet. You have the right number of electrons, but this one is better because it's more typical. So the typical bonding pattern is usually going to be a more stable or a better structure. So you got to do practice to find that typical pattern. We talked about it in class, how you can tell in the periodic table what the typical bonding pattern is. Which drawing is the polarity of methanol? So first we need to think about the polarity of the bonds. So we have dipoles and O and H. It's a polar bond. So which will pull electrons more, which is oxygen. So we can go ahead and get rid of this one and this one because the hydrogen is not going to be pulling down on the oxygen. It's going to be the oxygen pulling electrons up. And then, so we have to decide between these two, which's different. So the net dipole is up on both of them because we have a pull right, we have a pull left, we don't have any pull down. So the net pull is up in this direction. So you can imagine if everybody were actually playing tug of war, which way would the molecule actually be moving? It would be moving in this direction, right? Because if we had pulls this way and this way, it would move up. Now we have to decide, the only difference is these partial charges. So if the oxygen is pulling all the electrons, will it be partially positive or negative? It's going to be negative. So this one is wrong because this should be negative. Because if it's pulling electrons, it's going to be more negative. So that means that we're looking at option 2. Balanced chemical equation for the reaction. So I don't want you counting, when you see a diagram like this, I don't want you counting ratios. I want you just to write what's in the box. This box, if A is unshaded and shaded is B, then what's in the box? We have A2 in the box and we have B in the box. What's in the box? A, B, right? So let's find our reaction and maybe we can narrow it down from there. Well, oh, this is wrong. So it should be, it can't be B or C or A or B, so that's incorrect. The answer was written incorrectly. Um, it needs to be A2 plus B, and then we can balance it. Just balance it on your own. Don't look at the box. I think that when they put in these particle diagrams, it can be really confusing. Just balance it on your own, and get that answer. So the answer for that one should be D. Energy changes that occur in the forward reaction. So if we start here and we go down. So activation energy is what, and reaction is endo or exothermic. So remember, activation energy is the energy that you need to go from your reactants up to the top of the hill. So if we start at 40 and we go to the top of the hill, what's our activation energy? 10. And then endothermic versus exothermic is products minus reactants. So our products are at 20, or no, 15 minus reactants at 40. And we can already tell this is going to be a negative number. So if you want to do the math, you can, and you get negative 25. But because it's a negative number, that means it's going to be exothermic. That's your delta H. Right, so that's your delta H. So we're looking at exothermic and 10 kilojoules. What's the correct form of the conversion factor needed to convert number of moles of oxygen to number of moles of iron? So oxygen is 3, and iron is iron 3 oxide is 2. So we're looking for these two to be on top of each other. This one is iron and not iron 3 oxide, or it's asking us for the iron 3 oxide. Again, this one is iron. So this one is 2 to 3. Here's our answer. Oh, that's right. This is one possibility. So this one is a correct one, but we got to see if it's the correct one to convert moles of oxygen to moles. So we want to know how many moles of Fe2O3 from moles of oxygen. So if I start with moles of oxygen, I would need to put moles of oxygen in the bottom and mole Fe2O3 on the top. So that's why E is the answer and not C. But C is the correct statement. It's just not correct for this particular problem. And then again, we don't want moles of iron. We're looking for iron 3 oxide, which will cause the equilibrium to push to the right. So if we're pushing to the right, we can add, we can remove, we can remove. Basically, those are the three things we can do to push it to the right, right? Add away or remove, replenish. So add more NO2, yes. Remove O2, yes. Remove N2, all three. Which equilibrium constant represents a reaction that favors the reactant? So we're looking for the smallest K for reactants. So this one is the smallest one. Which changes will increase the amount of NO. NO is on the right, so we're looking for which way to shift it to the right. So we can add anything that's on the left side, remove anything that's on the right side, including heat. So decreasing NH3. If we decrease NH3, it'll shift to the left, so that's not a shift to the right. Increase O2. If I increase O2, it'll shift right, so that is a shift to the right. Decrease H2O, that'll shift it to the right to replenish, so that does increase it. Increase temperature, that'll shift it to the left, so that's not a number. So it's going to be 2 and 3. How many grams of carbon dioxide can you produce? So if we're starting with 30 grams of butane, which is C4H10, we need to first use the molar mass of butane. So 4 times 12.01 plus 10 times 1.008. And we get 58.12 grams per mole of butane. If you need help with any of these parts, please text me. We have 2 moles of butane per, what are we looking for? Carbon dioxide, 8 moles of carbon dioxide. And then for every 1 mole of carbon dioxide, there are 44.01 grams of carbon dioxide. And if you need help with this, please go back into the unit, find help videos, go back to the lecture videos, because this is really building on the dimensional analysis skill we were working on all semester. So we should get 90.8 grams of CO2. This question has appeared several times. Decreasing acid strengths, we're going to start with the strongest first. The strongest acid is the one that breaks into ions more. So HY is my strongest. And the next one that breaks into ions is HZ. And then HX is the last one. This is the weakest one because the acid stays together more in HX. It breaks apart completely in HY. There are no HAs together in this box. So the order is important for identifying acids and conjugates here. So we got to think about what's happening. So HSO3 turns into SO3. What happened? It lost H. So that's acting as an acid, which means this one must be a base. Now, if we want to reverse it, we can find our conjugates. So SO3 goes to HSO3. It added an acid, which means that's my conjugate base, and that's my conjugate acid. You can also think about just removing the H to get your conjugate base and adding the H to get your conjugate acid, whatever you want to think about, or you can reverse it to get your conjugates. But you got to find out which one's losing H, which one's gaining H. So we're looking for acid base, conjugate acid as the order. All right, think about electrolytes here. Electrolytes are how they break apart into pieces. So 100% break apart into pieces is a strong electrolyte, and don't break apart at all is a non-electrolyte. So it looks like A2X is a non-electrolyte because it doesn't break apart at all. A2Y looks like it breaks apart kind of half and half. And then A2Z breaks apart like 1 and 4. So 1 and 4 break apart. This one looks like 2 out of 4 broke apart and 0 out of 4 broke apart on this one. I'm just kind of looking at like these used to be together and now they're broken, and these used to be together and now they're broken. So this one is the strongest electrolyte because it breaks apart the most. How many molecules of O would we need? If we see molecules, you need to think Avogadro's number as a conversion. And if you see, so another Avogadro's number as conversion. So 56 molecules of C2H6. Now we could skip the Avogadro's number. If you notice that one you're going to be multiplying and one you're going to be dividing, you could skip it and just go straight to a mole ratio, and you can do like molecules. So we could say 2 molecules of C2H6 is equal to 7 molecules of oxygen. So remember that we can use that mole ratio kind of like a molecule or atom ratio as well. Or we could go all the way through and use Avogadro's number. And you'll find that when you do this, the Avogadro's number cancels out with itself. So when I put Avogadro's number on the top here, right, they would cancel out. So you get the same thing. All right, how many moles of iron 3 chloride between 4.6 moles? This is just a mole conversion. You don't need molar mass. So there are 3 moles of Cl2. I get that from the balanced equation. And we're looking for moles of FeCl3. And that's it. We don't need any mole masses or Avogadro's number because we are not looking at grams or tiny particles. Balance the reaction. So it's another one of these. Again, don't worry about the numbers. Just look at what's in the box. What's in the box? This is A2 plus B2 in the box. And this is A B3 in the box. So A2 plus B2 makes AB3. Now in the box, I know there's no, A2 is left over. So shaded spheres are A2. There's A2 left over. Now that's not a product, but sometimes we have reactant left over, which means we can know what is our limiting reactant, right? So if we want to balance this, we would need to do this. And then we know our limiting reactant is B2 because we have extra A2 left over because A2 is a shaded sphere. So that means that I don't need to even consider the A2 in the math. I only do math with my limiting reactant. So I have 1 mole of B2 and 1 mole of B2. It says how much product can I make? I can make 2 moles of AB3. So it'll be, why is this wrong? Unshaded spheres, shaded spheres. Right? Should be 2 moles of products. So A2 and B2 make AB3. And I balanced it 6, 6. Oh no, I balanced it wrong. This is why. This is why. This is this. There we go. Why am I getting this wrong? So this should be 3. Whoops. This should be 3 and 2, which is why we get 0.67. All right, there we go. So catalyzed reaction. First, a catalyst is not going to change reactants or products. So we can get rid of B and C. It's not going to change the whole thing. It's only going to change the hump. It's going to make it faster. Think about who's going to be faster. If you start here and then you make the hump smaller, it'll be faster. If you make the hump bigger, it'll be longer. Take you longer to get up the hump. So this one is going to be faster. So which could be a buffer? We're looking for a weak acid and its conjugate base, or a weak base and its conjugate acid. And so that doesn't have 2 things in it. The NAF doesn't have 2 things in it. Let's see. There's no acid or base there that we're recognizing in that one. So HF is a weak acid. So what's its conjugate base? When you get rid of H plus, you get F minus. That's your conjugate base. So we need HF with F minus, not H2O and not NaCl. So what does NaF have in it? It's F minus and Na plus. So that is what gives us that conjugate base. It's in there. It's just not the only thing because you can't only have an ion just hanging out. It has to have somebody it got electrons from. Which solution is the most acidic? So you can do a few different things here. You can solve for the pH of all of them. Or you can kind of just think about acid stuff versus base stuff. And so what I would probably do is just find the H plus for all of these. So your H plus is equal to your H3O plus, which is equal to 1 times 10 to the negative 14 over your OH minus. So I probably just do it for these 2, so I have it to compare to the first ones. divided by 1 times 10 to the negative 3. And if you know exponent math, this can be pretty easy. So remember, H plus and hydronium are essentially the same thing because they're 1-to-1 ratios in water. So most acidic is going to be the largest H plus, which would make the smallest pH. So that would be D. pH of 10 would be H3O plus of 10 to the negative 10. So, all right, number 47, if we have a 185-pound patient, this is body weight. 2.205 pounds of body weight is 1 kilogram of body weight. What dosage is this patient receiving in milligram per kilogram of body weight? Oh, I'm setting this up wrong. So we're looking for a fraction, milligram per kilogram. So let's start with our milligrams on the top, med, over our 185 pounds of body weight. And we need to turn pounds to kilograms, essentially. So we cancel out pounds by putting it on the top, since it's on the bottom. And again, that's body weight. And now we have left over milligrams per kilogram, which is what I want. So we should get 1.72 milligrams per kilogram. Which row has no mistakes? All right. Copper needs Roman numerals. Let me put this in a different color. So if we're kind of grading this, this would be copper 1 chloride. Calcium hydroxide, the name is correct. The formula is correct. So that one's right. Iron 3, that's correct. And nitrate, that's not the ion of nitrate. Nitrate is NO3 minus, not NO2, and definitely not NO2 minus. Ammonium does not have a charge of +3. Ammonium is NH4 plus. So that one's not correct. What's the charge on the chromium ion here? So if the Cl is -1, the chromium is what? We have 3 Cl. So -3 has to balance out 1 times what? And then we know our X must be 3. So it's 3 positive because we have to cancel out with a negative. Which represents isotopes. It's the same element, different masses. Mass number is the top number, top left number. So 15, so same atomic number. I know it's confusing because it's ABCD. It's not, these aren't actual, that's not carbon, for example. It's just like unknown ABCD. It's not actually an element. So it's got to be the two that have the same atomic number but different masses. So A and C. What is Q if Q2 plus contains 10 electrons? All right, so Q2 plus is 10 electrons. Now, how do we get to be a plus? We have to lose 2 electrons. So lose 2 electrons. So if I lost 2 to get 10, how many did I originally have? 12. Who has 12 protons? Yeah. Which are members of the ionic compound set insoluble in water? So ammonium is always soluble, so we get that out of here. Lead, sulfates are soluble, except for a few exceptions, that iron is not one. And then so this one is carbonates are mostly insoluble, and there's no exceptions there. Just look at your rules on your formula sheet, which represents hydrogen bonding. So hydrogen bonding, again, is intermolecular. So it's in between the molecule. So it would be this one. Wait, hold on. Yeah, one could be hydrogen bonding. Not this one, because this one is not. This is between the H. You have to have the H has to be bonded to an N, and the N has to be bonded, well, it doesn't have to be bonded to an H, but it has to be connected to an N with a lone pair, but let's just say it has to be bonded to the H too. This one, the N is bonded to the H, but the H here is not bonded to an H, it's bonded to a C. So that's different. This one, again, is not correct. Here, it won't be between the two H's because those would be positives. They would repel each other. Again, not between the two H's because those would repel each other. So red blood cells are placed into pure water. Pure water is 0% sodium chloride and 0% glucose. So that's hypotonic because isotonic is 0.9% sodium chloride and 5% glucose. So anything less than that is hypotonic. That O in hypotonic means it's gonna be swelling because the water is gonna flow into the cell because it's more concentrated in the cell. Look back at notes for that if you need some help. Electronegativity differences, which are labeled correctly. So not this one because nitrogen is more electronegative. Chlorine is more electronegative, and oxygen is more electronegative. So if it's more electronegative, it's going to pull electrons toward it, which means it's going to be more negative. So we put the partial negative charge there. Which relationship is incorrect? So a kilo is 1,000. That's correct. Deci and milli. So 1 deciliter equals 10 to the 1, 10 to the negative 1 liters, and 1 milliliter equals 10 to the negative 3 liters. And you could literally do a conversion if you wanted to. Just set it up. If you're not sure, if you're not good at the metric system, just set it up and see, is that 100 milliliters? But automatically I know this one's going to be incorrect. Why? You can't put a lot of big things in a small thing. A milli is small. We can't put a lot of bigs in a small. So the rest of them are actually correct if you want to check them out. But as soon as I see option C, I'm going to pick it and I'm going to move on. Which will make it shift to the right. So we can add something on the left or remove something on the right. So increasing the temperature, that would make it go up on which shift left. So not this one. Decreasing the temperature would shift it right. So yes, this one. Removing NH3 would shift it right. So yes to this one. Adding NH3 would shift it left. So no to this one. Removing N2 would shift it left. So no to this one. And adding N2 would shift it to the right. So yes to this one. So we have 2, 3, and 6. This is just a balancing question. So NH4, N2H4, H2O2, N2 plus H2O. We don't have any little tricks to pull here. We just have to count H's and O's. What I like to do is say if I have H's in multiple places, let's call these blue H's and let's call these green H's. We're going to add them up for the total. So let's start with our oxygens. We need to have 2 oxygens on this side. Give me 4. And I need more H's on the right side still. So I have to just move this number up to 3 because I still need more H's on the right side. So this is 6 and this is 3. Now I need more oxygens on the left side. So I got to put a 2 here. This will give me 10 H's and 4 here. So now I need more oxygens and H's. So I'll put a 4. We're just kind of going along here. Okay. Oh, I counted that wrong. This is, yeah, I added 6. That's 8. I was about to say. So keep track of it. I think separately, if you have elements in two different places, it can be more helpful to catch mistakes like I made there. And if you are not sure what to do, just say, well, I need more of this on this side. So just add a bigger number. Like you don't have to know exactly what numbers you're going to need at the end. Just put a number, see how it goes. Nuclear equation, what's the other product? So again, we're just adding the top numbers and the bottom numbers. Really simple. So split it in half. 245 plus 4 equals what? So 245 plus 4 equals, or sorry, 245 equals 4 plus what? So 245 equals 4 plus 241. So my top number is 241. Bottom numbers. 96 equals 2 plus what? That's going to be 94. So we're picking 241, 94. There's only one option there. And if we go look on the periodic table, number 94 corresponds to Pu, plutonium. All right, I think that's it. So let me know if you have any questions.